I'm going to talk just a little bit about motor control today, and I'm going to kind of stay at the low level. This is something we have gone through before, and so for the more experienced robot builders in here, this is all going to be redundant. However, there are some people in this room that know a lot more about this subject than I do, so feel free to interrupt me if I wander off target. The kind of motors we're going to talk about are brushed DC motors. In the world of DC motors, there's really two basic types. They're the three stepper motors, the brushed and the brushless motors. The brush motors, which is what most of us have in our robots, have internally a moving rotor which has the coils on it. You can see this one here I've disassembled. And then a fixed stator, where is it? Which has, if you can see inside there's a couple of permanent magnets. And then this thing here on the end is called a commutator. And the commutator essentially is the connections to all of these individual coils. And there's some brushes in there that press against these, and as the thing spins, it connects to a different set of coils. This particular one, if you look, the coils are slightly at an angle. They're helically wound. This is a kind of a fancy motor that allows it to run at a smoother, at a lower speed, so that you can get a little more torque at a lower speed. This one also has ball bearings, which is nice. Most of these, let's see if I have another, have bushings, bronze bushings, and this one has a ball bearing. The ball bearing can take quite a bit of axial load, whereas those little bronze bushings, which are very common, can't take much, just a couple of pounds. So if you're really going to mount a wheel straight on the motor shaft, which is one way of doing it, you need something that has ball bearing output. So the brushless motors, if you've seen those cordless motors, like the kind we use in the radio-controlled helicopters, are just backwards of this. The magnets are mounted on the rotor, on the thing that turns, and the stator, the fixed part that doesn't turn, has the coils inside of it. And there's a number of advantages to that, but essentially that's more like a multi-phase motor, a three-phase motor, where now the switching, instead of being done by a rotating commutator, the switching is done electronically by how you drive these coils. And I'm not going to talk about that today. It's a kind of a neat technology because, well, for a variety of reasons, but it's not what most of us use. That'll be another talk. This is kind of the standard DC motor. This one is a Pitman motor. Tanner's across the street has lots of used Pitman motors. It's always worth going over there and looking to see what he's got. Here's one I picked up recently, $13. This one's got a gear head and a motor and a shaft encoder on the back, and that was probably a $200 motor when it was new. So you can get these really nice motors. Somebody, I think it was Ray, said he's got some real nice motors from Palolu. Is that right?
Oh, no.
Was that James?
Probably James, but they're mpja.com. They've got some really good, motors with encoders and gear heads.
That's kind of what we're looking for. We'll just start here at the basic mechanical level.
Before you get too far,
sir.
Brushless, people use them for the quadcopters and stuff. What's the, if you know, what's the reason we haven't gone all over to brushless?
The controllers are a whole lot more complicated. Right. Most of those controllers can't give reverse, which we need for robots, although there are some. I've seen some boat controllers that allow you to give reverse. It's a very different technology. Essentially, you're pulsing this thing. The coils that you're pulsing are forcing the rotor to turn, and the coils that you're not pulsing, the field is collapsing, and so you read that collapsing field coming back, and you know how fast the motor's turning, and so it's an intelligent control. I assume that we will move in that direction.
Yeah.
But they're not that common now. They're pretty expensive motors. They have an advantage that they can generate a lot of torque at low RPM, which these can't. So we may end up going that way. So
they're a lot more efficient with the battery, how much juice they use as well.
Well, and really, you give the thing the RPM, and it says, I'm going to drive it at this RPM, I'm not going to drive it at a certain current. The motor will tell me how much current it needs to maintain this RPM. So it's got sort of this built-in feedback.
Yeah.
And so it's pretty cool.
Yeah.
They're pretty cool motors. But they're not on today's time. All right. So, okay, so that's, do I have a handy motor? I guess this one. So the way we're going to make this motor turn is by, we're going to drive a current through this rotor, and that current will energize one set of coils, and because of the permanent magnet, that's going to cause the rotor to move a little bit. And when it moves a little bit, that'll move it off to a different set of connectors here, and that'll connect to the next set of coils, and so forth. So driving a current through it will make the thing rotate. Here's a motor here. Here's a source of current. So, is that here where you can see it? So if we drive a current through the motor from this little 6-volt battery here, you can see the output of that gear head rotating slowly. If we reverse the current, we flow it through in the opposite direction, then the motor turns the opposite direction. So that's the basis of what we're going to do. We're going to control the speed by controlling the voltage. So we replace the 6-volt motor with a 12-volt motor. And in theory, battery. Thank you. Keep me honest over here. And it should, in theory, turn twice as fast. And same thing, we reverse that. And return. Now there's a tiny caveat here for those of you who've gotten into the foo of electric motors. They don't actually run exactly the same speed forward as they do backwards because of the way they're constructed. So if you put 12 volts into it and measure the forward RPM and then put minus 12 volts and measure the reverse RPM, they won't be exactly the same number. We can adjust for that in software, but that's just something to keep in mind. Okay, so generally we control the speed of the motor by controlling the voltage of the motor. And just a little tiny foray into the theory here. Each time you move that commutator a little bit, the previous winding collapses. In other words, you've energized a coil and generated a magnetic field, and that's caused the rotor to rotate. Now you move over to the next one, that magnetic field collapses, and the next one. When that magnetic field collapses, it generates a back EMF, a current back down the wire toward the battery. And the faster you go, the larger that is. So essentially you reach a point where no matter how much current you put in the motor, it won't go any faster because it's matching the back EMF. And that gives you the top speed of the motor. You put more power into it, put more current into the motor, it just turns into heat. It won't go any faster. So that sets the upper limit. You'll see it in the little course here. Have my Mark Rubio moment.
Yeah, good thing you're not running for president.
Okay, but everything else being equal, essentially, we'll have this this response curve. It won't be a linear one, which we'll get back to in a minute, that ends when the back EMF matches the current you're driving to the motor. And that sets the top here. Most of these motors, for our uses, for robot uses, the motors turn real fast with not very much torque. And what we want is low speed and lots of torque. We really would rather have a high torque motor. And the way you do that is by building a gear head. This is a, what does this one say? This is a 19-to-1 gear head. If you think, okay, I've got a motor that runs at 20,000 RPM. I want wheels that run at 200 RPM. So I'm going to have a 100-to-1 reduction. As you add the gear reduction, there's some efficiency losses, but essentially your torque goes up and your top speed goes down. So if you have 2-to-1, you'll have half the top speed and twice the torque. You're essentially spreading that over the same range. My experience with robots has been that we need something in like 20-to-1 to 100-to-1 range. If you're talking 100-to-1, that means your pinion gear is going to have maybe 8 teeth. It's hard to get much smaller than 8 teeth on a pinion gear because you end up with just a little star. And then 80 teeth on the spur gear, which is pretty good. That'd give you a 10-to-1. You need 800 teeth to get 100-to-1. Well, that's a huge gear. So typically the way that's done is in multiple gear stages. This one says it's about 20-to-1 and it does it with 2 gear. I guess that's 3 gear stages. And essentially what that is small gear driving a large gear, driving a small gear, driving a large gear. We'll power this one up, I think. We'll run with the gear head off. I'll turn it around here so you can see the gears.
close that view.
You see that the gear motor itself is spinning much faster than the output shaft is. And good gear motor, gear head is going to advertise. You look up the specs, they'll say, oh, this one's 83% efficient or 72% efficient or something like that, which means that part of that current you're driving in is using to drive the gear train itself. So you're losing a little bit just by driving the gear train to the output shaft. These that I use on the balancing robot here have a 60-to-1, is that right? Yeah, 60.5 to 1 gear ratio, which on the little ones that are built in here, they don't have shaft encoders on them, so they take a little more space. But that's about average, 60 to 1 or something like that, 50 to 1. If you want, for your own design, you have to take into account how big your wheels are, what's your top speed, what you want your top speed to be, and then you work backwards from there to figure out what kind of motor I need, what kind of torque. Generally in robotics, we're not interested in high speed. We're interested in torque. High speed just gets you in trouble. You don't want a robot faster than you can chase. I think that's enough. So, on to the H-bridge. Okay, the way we control these things, now I have to do a drawing. Actually, they want something to screw up here. We have our motor, and we have a minus and a plus input to it. And up here we have the V plus of our battery. Nice and noisy board here. The reason this is called a H-bridge is somewhat obvious. It looks like an H. And we've got 4 switches here. We're going to label these. This is our left side high switch and our left side low switch. This is our right side high switch and right side low switch. So imagine for the moment that these are just physical switches that we're going to throw in our hand. If we wanted the motor to go forward, in this case, we would say we're going to set our left hand upper switch and our right lower switch. All right, so we turn those on and we get current that goes like this and drives the motor forward. If we want to drive the motor backwards, we open those 2 switches and we close these. So here's forward. Backward, we're going to say right high, left low. So, as complex as this can all get, that's really all it boils down to. There are several other permutations of this. So let's go through them. First one is, suppose we closed the lower left and the lower right switch. So now essentially we have both sides of the motor connected to ground. And that's how you do dynamic braking. So we'll call that braking. And we want both low sides turned on. All right? But if we turned on both high sides, so the motor is effectively disconnected from ground, that's how you do regenerative, you recharge the battery, you do regenerative braking. Now, this is almost never used in robotics, but it's another logical option here. So we'll call that regen. We're going to have both high sides.
Will that give you braking?
Yeah. Essentially, when you're using the braking to charge the motor.
No, that configuration won't charge the motor.
This one will not?
No, something's wrong.
Okay.
'Cause
All right,
think about
ignore
it.
this one.
Yeah, think about it. There's no path between the battery. Is a path between ground and V+. If you drew that over there, there's no path in that configuration. So something's wrong.
Okay. As I say, it's never used in robotics, so maybe that's why. It doesn't actually work.
Yeah, you'd actually
Well, there is a way to
disconnect
do
the
it.
ground and send it to the other side, right? You have a path, you don't, you get a real path.
You could have a diode
Yeah, or something.
that would allow a path from the motor to the battery and not
Maybe that's
back.
what's required.
That's what would be required.
Yeah.
But yeah, that would also be a braking. Okay.
There's two others, which I'm going to call fire. And that would be if you had the left high and the left low, or the right high and the right low.
That'll start a fire?
And that will start a fire. Because now you've hooked your battery
Shorted it out.
straight to ground. Okay, so obviously there's some of these to be avoided. There's another pin that we'll get to it in a moment. But typically, what you'll see, the way these are actually manufactured or built, is that there'll be a control for these two sides, and one of them will be inverted, which I'll signify with this little. Same thing here. All right, so you're actually not going to control all four switches independently. You're going to control these two pins. And when you turn this one on, this one will close and this one will open. You can't ever have both of those closed. You just prevent it in hardware. Furthermore, you want this switch to be really fast because you don't want there to be any time at all in which both of them are on. Those of you who know about switching know we always draw these things like that, but that's not actually what they look like. If you zoom in on them fast enough, they look like that. There is some time in which this one and this one will both be on. There's some, there's some cross point there. You just want that to be really, really fast, really, really small. So, and this isn't the way it has to be done, but this is the way it's often done. All right, there's one other input that I'm going to draw down here just at random. And it's an enable, which enables this whole circuit. So we have our pins to turn these on and off, and our pin to enable the whole thing. Is that pretty clear? There's a lot more to go into there, but I just want to, for those who might not have seen it, the basic architecture of it. Okay, there are various ways of actually implementing this. A typical one, let's see if I got a sample here, is we'll actually do it out of discrete components like I've drawn up there. Here's one made by Devon-Tech. This is a real nice one. And you can see that there's a set of, I guess those are little MOSFET switches there that actually do the switching. There's a microprocessor on there. This one's got an intelligent front end. And this is a 2-channel, so you put power into it, power 2 motor, so it's actually a pair of these. There are also a lot of integrated circuits that do the same thing. This is a L298 chip, which is a very common, I think it's a 1.5 or 2 amp chip, something like that. So for the kind of motors we use, that's fine. And you can find lots of little kits out there that'll be $6 or $7 or something that have a 298 chip and some connectors and these high-speed diodes here for that you have to have for the switching transits and so forth.
Well, you say we commonly use the 1 amp, but you gotta watch your stall current. So it's your stall current, not your running current. You gotta look at the current phase.
And Richard makes a good point, which is we take a motor like this and essentially just measure the resistance when it's not turning. Then that's the voltage you put in that divided by that resistance is the current that this thing is going to require when it's stalled. Electric motors are interesting in that they have the maximum torque when they're at 0 speed, when you're just trying to turn. So you have to be sure that whatever device you're using, you say, well, it turns out our stall current's 2 amps and this is a 1 amp device, this is not going to do. This might help.
There you go, 2 amps.
Yeah. Put a heat sink on it. I have one of these on my big outdoor robot that's got an enormous heat sink on the output, and I think these things are good up to 5 amps or something like that, which is way more than I need. Just by way of comparison, this robot, which runs off a 24-volt battery and uses these motors, typically when it's running around draws about 300 milliamps. So we'll say 12 watts or something like that. It's an advantage that you go to a higher voltage because for the same amount of power you have less current, since we have current limited devices, but they're not voltage limited. So if you're going to 12 volts, you'd have to have twice as much current than at 24 volts. Also, lots of these industrial motors are 24 volts. I'm not sure why, but that's just very common. So, the TI makes a chip that's pretty popular called L295. It's a little bitty integrated circuit that I think can drive a half an amp or 500 milliamps or something like that. So this is like basic bare bones hardware controller. There's also a step up from that, and actually this Devantech is one, which is H-Bridge has got a microprocessor built into it that can do things for you. Pololu makes one called the RoboClaw, which is really nice part. SparkFun has a bunch of them. Generally, they have serially or I2C or something like that, and you can do all kinds of programming in. That's very common now. Rather than just buying the raw H-Bridge, you buy one with a microprocessor that does stuff for you. And
Including count your encoder ticks and
yes,
things like that.
You will
Run
get
your
to
own.
it, yes. That PID controller and yeah, all this other stuff. So, okay, so enough with the hardware. We're actually going to control this hardware with something called pulse width modulation. And because we're controlling the speed of the motor by controlling the voltage, if we can vary the voltage, we can vary the speed of the motor, which is what we want to do. This thing allows us to drive the motor forward and backwards, but it doesn't do anything to control the speed. It's just going to run it full speed. So with pulse width modulation, what we're going to do, and there's a couple of different ways to do this, is we're essentially going to rapidly turn on and off the voltage to the motor. We're going to send it a pulse rather than just a DC. And the inductance and the mechanical inertia of the motor itself will serve as a smoothing filter for that to give us our voltage. So just to be clear, we're going to send it something that looks like this. We'll talk in a minute about what the frequency of that is. So this is a pulse width, and this is about a 50% pulse width. That is, it's on about half the time, and off about half the time. So we call this 0 volts and whatever, volt plus. If we were to do the same thing and say we wanted a 10% pulse width or an 80% pulse width, so even though what we're sending it is a pulse, when you send this through the filter of what is the motor and its mechanical and electrical characteristic, what you'll get out of it is something that looks very much like here. If it, if this was 0 to 10 volts, this would look very much like a 5-volt signal. It would be a little wiggly. This would look like whatever that is, a 1-volt signal, an 8-volt signal. But what we're actually driving through is this pulse train. So while we can say that if this is 0 to 10 volts, we'll say 0 equals 0, and 50% modulation equals 5 volts, and 100% modulation equals 10 volts. And that's the way we could think of it. And point of fact is not linear, as you would expect. The response between voltage and RPM is really not linear. On these DC motors, it's not RPM that's proportional to voltage, it's torque that's proportional to current. And RPM is going to determine what the load is and so forth. So it's not that simple, but if you were to draw an graph of it, where we had volts on this side and RPM on this side, then it's not a nice straight line. It doesn't come on for a little bit, and then it suddenly jumps on, and then there's a very steep rise at the end. So this is as you're approaching that point where the back EMF matches the input voltage, and this is essentially as fast as you can go. So it takes quite a bit of change in voltage to get from this speed to this speed as compared to get from this speed to this speed. There's a couple of ways you can deal with that. One way is you could build a lookup table, and some of my robots do that, where you're just going to calculate what's the actual value needed to produce a linear ramp, and look that up in a table when we write the PWM value. Another way to do it is to use a controller that actually is a chopper that's actually controlling current rather than voltage, and then we actually can have a linear relationship. But the easiest way to do it is to use a PID controller, and that'll linearize the whole thing. We don't worry about it anymore. That way the motor can have any arbitrary response and it'll end up with a linear output. So, clear there. I'm just, as I say, I'm just covering little bits and pieces of this. I'm going to be sure everybody's all right. So, how do we control this H bridge? A raise bar. We have to generate this pulse somehow. Now, if you've got a H bridge that's got a built-in microprocessor on it, it probably generates that pulse for you. So we're going to assume that you're trying to build one of those, and you need to know how it works. So essentially, you can specify these either, depending on how your hardware is set up, either you tell it a low time and a high time, or you tell it a frequency and a pulse width, or a duty cycle, I should say. That's an easier way to specify it. And so, in both cases, essentially we have a duty cycle and we have a frequency. So what is that frequency? How do we come up with that frequency? Well, it turns out that it has to do with the motor itself, and so it's going to vary from one motor to the next, and with the way you're driving it. You want the frequency to be high enough that the mechanical inertia and induction of the motor smooths it out. If it's too low, the motor will be really rough. You want it to be low enough that you don't run into these switching problems. Obviously, if you were switching at this speed, you'd spend all your time in that transition, so you can't be that high. You have to stay down within the switching. Also, there's an annoying audio component of this if it's in the audio range. So most of us can hear from about 50 hertz to about 20 kilohertz. If you're above 20 kilohertz, you won't hear it. That's best. If you're around 1,000 hertz, that's really annoying. That'll sound like a needle pushing into your eardrum. It's obnoxious every time the motor's turned on. If you have to have it in the audio frequency, you get it down around middle C, which is about 250 or say 500 or something like that. At least it's not annoying. It'll have a but it won't be piercing your eardrum. So if you have the PWM frequency too high, one of the things you'll notice is that when you start turning up the pulse width, you get up to 20 or 30% pulse width, and the motor hadn't turned on at all. You finally get to about 40% pulse width, the motor starts turning, and then it starts turning rapidly because you're too much in this range. So if you find that happening, drop your pulse width frequency down until it should come on at about 2% or something like that. The motor should come on. Okay, there's two basic ways of doing actually there's a whole bunch of ways of doing PWM, but there's two very common ways of doing it. The first one's called sine magnitude. And the sine magnitude, I'm going to draw our H bridge up here. This is just a single channel. We have direction and enable. The sine magnitude, what we're going to do is we're going to drive the enable pin with the pulse width. So we're actually switching this on and off. And we're going to drive the direction with the sine. So if we have, let's say, arbitrarily, let's say our control goes from minus 100, which we'll say is minus full speed, through 0 to plus 100. So what we'll do here for sine magnitude is we strip off the sine, and we use it to control this speed. And we use the pulse width to control the modulation. Now, there's a couple of things to realize about this. I'll come back to them. The second common way is called locked antiphase. Locked antiphase, what we're going to do is we're going to just hold the enable pin high. We're going to drive the pulse width signal into the direction pin. Okay, so what that means is that the direction of this thing is going to be switched back and forth at the pulse width frequency, at the pulse width modulation frequency. If we're at exactly 50%, then you're going to be going forward and reverse, and the currents will cancel each other out, and we get 0, and the motor doesn't turn. So in this case, 0 represents minus full speed. 50% represents 0, and 100% represents plus full speed. So in practice, what you do is just scale this one into this one. So we'll say, if we're using locked antiphase, we'll say voltage is equal to, let's see, I got it written down here. Duty cycle, here we go. Not voltage. So duty cycle is equal to duty cycle plus 100 to. So we can still use this minus 100 to plus 100, and here 0 is still 50%. Now there's a couple of differences between these two that are interesting to note. When we're running sine magnitude, on the negative part of the pulse, we have disabled the jet. So the wheel is effectively freewheeling or coasting during the negative part. We're being driven forward or backwards in the positive part. With locked antiphase, in the negative part of the pulse, we're actually driving in the opposite direction. So the wheels are very much locked. That is, you can demonstrate this here. If you fire up locked antiphase, it's real hard to turn the wheels. That is, when it says 0, it wants to stay at 0. Whereas with sine magnitude, 0 is 0, you can turn the wheels. So, and they use electricity in a different way. They use power. See if I can demonstrate here. With this guy, and then I think we're ready to set up robots. Okay, what I've got here, a knob, and I've got this knob set up to control the pulse width, and I'm sending the same signal to each wheel. Well, just turn it on and tell it to go, and give it a very small, oh, didn't I tell it to go? I didn't tell it to go. Well, okay, I'm doing something. See what I get for not testing?
It worked at home.
It worked at home. It worked at home is our logo, our motto.
Just because I always say that, right?
Yeah.
Well, I can't make it work, I'm sorry.
Would help if we count down from 10 and give you 10 more seconds. 10, 9, 8.
All right, it's not working, so I just have to tell you what it was going to do. I was going to show that when I just ran the raw PWM signal and the robot moved across the floor, but if you grabbed it, it would just stop. If you turn the PID on and do the same thing, let the robot move slowly across the floor, when you grab it, it tugs real hard because it's trying to keep the wheels going at the same speed, and you're actually asking for more torque. So, and that's a cool demonstration. I'm sorry it doesn't work. But with that, I think that's all I'm going to say today. There's one last little piece which is useful when you're actually controlling a two-wheel robot like this, where you actually have two H-bridges, two motors, and two wheels, and you normally control the thing in terms of a left and a right velocity, but that's actually pretty clumsy when you're trying to write high-level software. So the last point is that we define two values up here where I can see, which we're going to call, rather than currently we have left and right, instead we're going to have velocity and rotation. Where velocity is the speed at the center of the robot, right here, irrespective of what the two wheels are doing. For example, right now the velocity would be 0. And rotation is the rotational velocity around the center of the wheel. So if your high-level controls talk in terms of velocity and rotation, think of it as speed and steering. That's a whole lot more easier to work with than trying to figure out how to get the right turn by a combination of left and right wheels. And the calculation is easy. When you're done, you say, my left is equal to the velocity plus the rotation. And I actually go to control the motor. The right is equal to the velocity minus the rotation. And that's what I had these little knobs set up here to do. And I think with that I'm done.
John's an expert at
We're on
the course now, so I'm good.
You're gonna win.
3 seconds.
All right.
Resell life.
Wait.
What we're talking about here is closed loop control, which means that we're no longer just going to write a voltage or a pulse width and send it to the motor. We actually want to know what the motor's doing, and we're going to use that to send it. So closed loop control means that you have some kind of feedback, and feedback in our case is the encoders that are on the motor. And what they're going to do, these are quadrature encoders, so they tell us which direction the motor is going, and they produce a tick ever so often. I think this one produces, oh, it's got 128 ticks per revolution or something like that, the encoder. So what we have to, we have to have an encoder. We have to have one on each wheel. So we'll say encoders. We have to sample them at a periodic rate. Okay, this is really important, because what a PID controller really is a filter. And for those of you who know filter theory, if we don't sample at a constant rate, we have to know the sample rate. We have to know DT. We have to know how much time has elapsed. And send that forward through all the equations. But if we can sample it at a constant rate, we can ignore that. And that just makes all the rest of the math much easier. Generally, in everything that's running in the robot, if you can do everything at a constant rate, a constant sample rate, a constant control rate, that makes everything easy. So you have to do it periodically, and it has to be precisely periodically as best you can do. Now, what is that period? Well, a lot of that depends on what you're trying to do and what the specs of the encoder are. But let's take a simple example. Let's suppose that our update rate, that is the robot is reading its input, it's doing some calculation, it's writing its output. Let's suppose we're doing that at 10 hertz to make the math easy. And let's suppose we have an encoder that at full speed is returning 1,000 counts per second. So that means at 10 hertz we're going to get 10 counts. So that's full speed. Let's define slow speed as full speed over 10. That's a good number. So full speed in your car, 70, slow speed would be 7. That means that we're only going to get one tick in that period window at slow speed. One tick's not enough. Really, you need about 10 ticks. So the size of your sample window, the size of the number of encoder ticks you're going to get, how often you're going to update. But here's the rule. The more ticks you have, the better. It's hard to do smooth control if you only have 1 or 2 counts. But if you got 500 or 1,000 or more than you need, big deal. we got microprocessors that can handle it. So more ticks is better. On my robots, this one the update rate's 25 hertz. This one the update rate's at 50 hertz. So he has less time to gather encoder ticks, but he has much higher resolution encoders. This one has these hand-built encoders that only have 25 counts per revolution, so I can run it at a higher speed there. Okay, so this is our feedback for our closed loop. All right, and then the PID algorithm itself, which stands for proportional derivative and integral. And ignore these two terms right now. Proportional means what we're going to do is we're going to, each time around our control loop, we're going to measure how fast the wheels are going, and we're going to compare them to how fast we ask them to go. We're going to subtract those two, and we'll get an error. So, make sure I get these in the right order here. So, our proportional error is the requested speed minus the measured speed. All right. These other two are derived from this. The derivative is this proportional minus the last one, which we saved last time around. And the integral is just integral plus equal proportion. All right. So take a simple example of that. Say we ask the robot to go 50, and the robot's actually going 40. So 40, 50 are requested, minus 40 are measured is 10. So that means that we're going to add 10 to whatever our current control function is in our integral. We need to increase it. Okay, suppose we measured, we asked 50, but we measured 60. We're going too fast. This number will be negative, right? Negative 10. We need to subtract something. So we're no longer going to tell the motor the speed we want. We're going to tell the PID controller the speed we want, and it will adjust the PWM up and down to get the speed, which is pretty cool. As I say, I'm really sorry I couldn't get that to work. There are 3 games, actually 4. There are 3 games that we use to control this with. I'm going to call them K. So we have a K proportional, and a K derivative, and a K integral. And those are how we're going to scale these values. And then I have to have a chair. The standard PID algorithm says V out, or voltage out, is equal to the proportional error times its gain plus the derivative error times its gain plus the integral error times its gain. And that's it. Now, the hairy part, of course, is setting these numbers, setting the gains. You can come up with some arbitrary numbers to start with. Generally, to tune one of these things, what you do is you set all these to 0, and then you start increasing this one and until the system starts to oscillate. And then you start increasing this one and backing off on this one until the oscillations go away. And we'll come back to the integral in a minute. There's not really a correct way to tune it. That is, when it's operating properly is when you're happy with it, right? So you can tune it, you can make it really tight so that the robot's responses are real quick and really, you can make it really loose so it's much more organic, if you will. That's a matter of aesthetics. There's no one to say that's the right way to do it. You know, you do it until you're happy with the way it is. There's 2 really basic types of PID control. There's, at least as we use them, there's a position PID and velocity PID. And there's one other term I didn't include in here that I've actually been playing with. It works pretty cool, which is a feed-forward term. So for the feed-forward term, we're going to add one more constant here. And we're going to say this is plus our requested times its constant. What that does essentially is it gives you a cheat on getting to the set point. You get to the set point real quickly, This guy takes you right there, and then this guy adjusts you around the set point. So the position PID essentially is that you're calculating the position of the robot, and you want to offset that position. When you use this, the error is the difference between the position you want and the position you have. We'll call that position PID. And the other one is velocity PID, which is mostly what I use. The velocity PID, your output, V out, plus equal pro times Kp plus derivative times Kp plus
What's the last term there?
that's the feed forward.
The feed forward.
Yeah. So if you look at what you're doing here, you're actually accumulating the output. So you think about this output as like your accelerator pedal. Imagine you had a lever that you're using to control the speed of the motor. And what you're really interested in is the position of that lever. So when you find the optimal position, the motor's going the right speed, then the difference between requested and measured will be 0. And the derivative will be 0, and the feed forward will ignore for a minute. You have to handle it differently. So you won't affect this anymore once you reach the set point. That's an easy one to get working. There are some other things that would have to be taken care of. So, as I say, essentially the way you tune any of these is to set it all to 0, and you increase the propulsional error until you get oscillation, and then you back off on it and increase the derivative. And then the integral really is to take care of long-term errors. So if you're always drifting right or you're always drifting left, the integral will take care of it. Okay, that's all I have on PID.
No, that's some good stuff. I mean, we should tell everybody you could spend days and months and years tuning a PID algorithm.
And for
If you
those
want to fool with it.
mathematicians in the room, you know, they take these things and they generate these three-dimensional surfaces. And they say, you know, over here there's this pole that goes off to infinity, and over here there's this hole, and you stay right here in this part of the map, and you're in the more or less linear range. You know, it's not as simple as it might first appear. I think that's all I got.
All right, awesome. Thank you very much, Dave.